In this example, we're building LC circuits using inductors drawn from a normal distribution and capacitors whose capacitance is drawn from a uniform distribution. The result of putting these two components into our circuit is that we get the resonance frequency, this omega naught value, as going to change depending on the specific value of L and the specific value of C that we're using. So the premise of this, in reality, what we would be doing is have a big box of inductors that we'd be randomly picking one from. It's going to have an inductance with a mean value of 1.5 Henry and a standard deviation of 0.07 Henry. And then we're going to have another box filled with capacitors, but the capacitors have a uniform distribution, so we're equally likely to pick a capacitor between 400 microfarad and 800 microfarad. So what we want to do is see how these two components are going to affect the resonant frequency. So the first thing we want to do is create our components. So first, what we can do is create our inductors. So again, it's a normal distribution with a mean of 1.5 Henry. So that means the mean is 1.5 plus our standard deviation times rand n. And I'm going to start by just using 1,000 samples, and we'll see how this is going to affect our answer. So I'm going to create 1,000 inductors. I want to be plotting these because this is going to be normally distributed. I can use the Rice rule or I can use Sturgis's rule. I'm just going to use the Rice rule for this to see how many bins to put in my histogram. So it's a ceiling of 2 times the nth root of really SAMPS, and I want the third root there. Right, so it's going to make, in this case, 20 bins. And if I make a histogram here, just to make sure that we're doing this correct, of my inductors, we see that familiar bell-shaped curve that we expect since this is normally distributed. Right, now I can also make my capacitors. This comes from a uniform distribution, so I don't want the rand n here. I have values between 400 microfarad and 800 microfarad. So for the uniform distribution, I want to take the lower extreme, so that's the 400 microfarad, plus the range, in this case 800 minus 400 is also 400 microfarad, times just rand for a uniform distribution. And I want that to be 1,000 random numbers here. All right, and just again to test this, I want to look at the histogram now of my capacitors. And we see more or less, we're only using 1,000 samples here. We'll see if that's enough in a little bit. But we see it's more or less uniform compared to our inductors that we just saw before. We have our inductors, we have our capacitors, so now what we can do is calculate all of the resonant frequencies. So again, each circuit we build is going to have a different resonant frequency because we're randomly selecting one inductor, we're randomly selecting one capacitor, and putting it together in our circuit. So in this case, we're going to have 1,000 different resonance frequencies, one for each circuit that we're building. So that's going to be 1 divided by the square root of each inductor we choose times the capacitor we choose for that. So again, the first inductor will go with the first capacitor, the second inductor with the second capacitor, and so on. So we'll come up with 1,000 resonance frequencies here. Okay, and we see in our workspace that W naught is 1,000 values. So now what we can see quickly is a histogram. How are the resonant frequencies distributed? Clean this up a little bit, put on our grid. This is our omega 0, and this is in radians per second for this. And right now I'm using a non-relative histogram, but I'm just trying to look at the shape for right now is my main concern. So we see it does not look normally distributed, it doesn't look uniformly distributed. That's because we're multiplying a value that comes from a normal distribution and one that comes from a uniform distribution, so we can't necessarily, without going further into the math, predict what this shape was going to look like. And we're going to use more samples in the future, but this is our rough shape for the distribution of our frequencies. So it doesn't appear to be normally distributed, but I want to come back to this in a minute. I want to make sure that I'm using enough samples here. Is 1,000 enough samples? So what we can do to test generally, do we have enough samples, is we want to track a common thing is the mean value of our output, in this case our omega naught. So what I can do is I'm going to make something called M, which is just going to track the mean value of omega naught. So what I'm going to do is I'm going to see what's the mean if I only use one sample. The mean if I use the first 2, the first 3, the first 4, the first 5. So I'm making all 1,000, but I'm testing the mean by subsampling this from the first, then the second, then the first 2, then the first 3, etc., all the way until what if I use all of my samples. And then visually we'll be able to see, are we using enough total samples? Right, so I'm going to take the mean just of the first k values of omega naught. So 1 to k. And that should be 0. And if I run this, so now I have my M, and we can look at our convergence here by making a semi-log plot in x of omega 0. Sorry, well, not omega 0, but M. That's the plot that we're interested in. All right, so we see here, that's typical for convergence plots, is that the more samples we have, then the value of the mean here, let me put some labels on. So in this case, our horizontal is the number of samples. And in this case, our vertical axis is the mean value of omega 0. And I want to look at with the grid for a little bit more detail here. So what we see that's typical in most convergence plots is that the mean is going to shift around here, and then eventually it's going to come and kind of settle in to a value. And we see here it kind of does that as we get to 10 samples and then we get to 100 samples. It's fluctuating less, and there's different types of criteria we could have that's changing less than 1% or something like that. But here, we're not seeing it really go into a flat section, which is going to be typically what we want to see to declare that we have convergence. So I'm going to say here 1,000 samples is probably not enough. So let's see what happens if I put 50,000 samples. Let's see the difference in this convergence plot that's going to come out. So we see here, let me tighten up the axes. And rerun this. So now we see more what we're looking for. See here, once we get to 1,000, it starts to flatten out, but by the time we get to 10,000 here, this line, this mean value, is really unchanging. The more and more samples we include, it no longer is really shifting the mean value we're finding for omega naught. So I would say for this one, once we get to 10,000 samples, that we've reached convergence for this particular sample. So this answers the second part of the question. We have enough samples. I, in this test, ran 50,000, and we see from the plot here that around 10,000 will have enough samples. Now let me go back and answer question 1. I want to now look at this histogram where I'm using 50,000 samples. And now we see we get a lot more detail of its shape. It does not look like that normal distribution. It doesn't have that nice bell shape. And it's not a uniform distribution, certainly. It's this other looking distribution here. But what we can do is we can test, is this normally distributed? And we can use that Lilly test on what I'm calling omega 0 or W0. And we don't, by looking at the shape, we should not expect it to be normally distributed. And when we run the test here, we get an H value of 1, and we get a p-value much, much less than 0.05. So by the Lilliefors test, this is not considered normally distributed. We should not consider it as a normal distribution. So that answers the first part, and we already answered the second part of the question. Now what we can look at is how many what percentage of our circuits are going to have resonance frequencies between 40 radians per second and 30 radians per second. So if we looked at a normalized histogram, we could look at the area under that shape. This is not normally distributed, so we can't use the nice built-in norm CDF function to do this. But what we can do is from our sample data, we can see what percentage of all of our simulated circuits are going to fall between 30 and 40. And then we can kind of expand that out and say that in our manufacturing process, if these were the components we were using, we would expect that same percentage of all of our components to have resonant frequencies between 30 and 40 radians per second. Right, so in this last part here, I'm going to call it good for right now. I want to look at all my omega zeros that are less than or equal to 40 radians per second. All right, so if I run that, I see good is just ones and zeros here. Again, this is a logical test, so omega naught has 50,000 values. It will have a 1 if it's less than or equal to 40, and a 0 if it does not have less than or equal to 40. But not only do I want it to be less than 40, I also want it to be greater than or equal to 30. So this AND here is going to give me a 1 if both of these things are true, and a 0 if either one is false. So if I rerun that, we see good has, again, ones and zeros here, and right now it's 50,000 elements long. So to see what percentage of them fall between 30 and 40, since good is only ones and zeros, and 1 means that it falls between 30 and 40, if I take the sum of good, it adds up all those ones together, and I get 40,320. So of all 50,000, 40,320 fell between 30 and 40 radians per second. So finally what I can do is if I take that over the total I had, which was 50,000, and I can multiply it by 100 here, I see that I can expect 80.64% of my circuits to lie between 30 and 40 radians per second for their resonant frequency. Again, we want to be careful. This number is going to be affected by how many samples we're using, and that's where the convergence is really crucial. Let me take a step backwards actually here. Let me go to using fewer components again, back to only 1,000. If I rerun this whole section, I see here that my estimate is that 79.2% of my circuits lie between 30 and 40 radians per second. And that's different than what I just saw before. So when I reach convergence, I can be more certain that the value I'm getting is going to be correct, or it's going to converge to what's the correct value is going to be. So again, we have convergence, and we get a very similar number, 80.6. Going back one more time to using fewer samples here, if I keep rerunning this with fewer samples, I get 81.7. If I rerun it again, 81.2, 80.2, 80, we see that the percentage keeps changing fairly much if I use too few of samples. But if I keep it with a high number of samples where I have that convergence, what I should see is that estimate at the end there of what percentage of the components lie between 30 and 40, that should be fairly consistent. So yeah, I keep getting about 80.6 when I use 50,000 samples here.